Chapter 9, Section 3, Relative Rates of Growth. Say that you have two functions and you want to know which function grows faster as x approaches infinity. What you do is make a fraction with the two functions. Make one of the functions the numerator. Make the other function the denominator. We calculate the limit of this fraction, or this ratio, as x approaches infinity. One of three things will occur. When you calculate this limit, you're either going to get infinity, 0, or some number, not infinity or 0. You might get infinity. If that's the result, then whichever function you made the numerator grows faster than the other function. If you get 0 when you calculate this limit, then whichever function you made the denominator, whichever function you put on the denominator, grows faster than the other function. And if you don't get either of these, then we say the two functions grow at the same rate. So if you put one function over the other, doesn't matter which is which, just one of them will be the numerator, the other function will be the denominator. Take the limit of this fraction as x approaches infinity. If you get a limit, not infinity, not 0, then you say these two functions grow at the same rate. And all of these sentences end with the phrase, as x approaches infinity. Page 461, exercise 18. The question is, determine whether this function, x times e to the x, grows faster than e to the x at the same rate as e to the x, or slower than e to the x. The question is, does this function grow faster than, slower than, or at the same rate as e to the x as x approaches infinity? What we do is put this function over e to the x, or vice versa. It doesn't matter. I'll put the one I circled in red over the e to the x, and we're going to get the limit of that ratio as x approaches infinity. That would be the same as the limit of x, because of canceling, as x approaches infinity. And obviously the limit of x as x approaches infinity is infinity. So when that happens, we have a function over another function. The limit of that as x approaches infinity is infinity. Then whichever function we wrote on the top grows faster than the one that we wrote on the bottom. So the conclusion here is the function that we wrote on the top grows faster than the one that we put on the bottom as x approaches infinity. That's our answer. Next one is number 20. The question is, does e to the x plus e to the negative x over 2 grow faster than, at the same rate as, or slower than? It's one of those three, comparing to e to the x as x approaches infinity. Does this function, the question is, does this function grow faster than e to the x, slower than e to the x, or at the same rate as e to the x? You put this function over e to the x, or vice versa, it doesn't matter. I'm going to put the red function over e to the x, e to the x plus e to the negative x over 2. That's the function that we're being asked about. We're being asked to compare it to e to the x. And so we need the limit of this ratio as x approaches infinity. We're either going to get infinity, 0, or some number other than 0 or infinity. Well, the numerator, that means above this blue line, can be multiplied by 2, as long as we multiply below the blue line by 2 also. So this fraction simplifies to this blue one. Multiply the numerator and denominator by 2. That means we have the limit as x approaches infinity of e to the x plus 1 over e to the x over 2e to the x negative x is the same as 1 over e to the x. And let's multiply above this yellow line right here by e to the x. Multiplying the numerator of this fraction by e to the x is e to the 2x plus 1 over 2e to the 2x that's the same as the limit as x approaches infinity of e to the 2x over this denominator plus 1 over the same denominator. We have the limit as x approaches infinity. E to the 2x over 2e to the 2x is 1 over 2. So now we've done a lot of algebra, lots of algebra here. This limit ends up being a half, because if x is very, 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 very large, e to the 2x will be larger, e to the 2x will even be larger, 2 times that even larger, and 1 divided by that is 0. 1 donut divided by this denominator, 0. So, summary. We put this red function over e to the x. We found the limit of that ratio as x approaches infinity, and we did not get 0 and we did not get infinity. That means these two functions, the one in the red circle and this other one in the red circle, it means they grow at the same rate as x approaches infinity. So I'm going to write the answer down here. Summarize this problem. E to the x plus e to the negative x over 2, and e to the x grow at the same rate as x approaches infinity. This function does not grow faster than e to the x, and it does not grow slower than e to the x. All right, the next one is number 22. The question says, determine whether 15x plus 3 grows faster than at the same rate as or slower than x squared as x approaches infinity. This is exercise 22. Does this function grow faster than x squared, slower than x squared, or at the same rate as x squared as x approaches infinity? Well, we make the limit of the function here, 15x plus 3, over this other function, x squared, as x approaches infinity. We'll get one of three things will be the result of this, either infinity, 0, or some number other than 0 or infinity. We find this limit using the divide every term by the highest power of x. So we're going to divide each of these terms by x squared. 15x divided by x squared, 3 divided by x squared, and x squared divided by x squared. That's equal to the limit as x approaches infinity. 15x over x squared is 15 over x. 3 over x squared is 3 over x squared. X squared over x squared is 1. This limit, the limit of this, as x approaches infinity, is 0 plus 0 over 1, which is 0. Put that over here. We put one function over the other. The limit as x approaches infinity came out to be 0 this time. That means whichever function we put on the denominator grows faster than the other one, faster than the one that we made the numerator. That's what we say when we get 0. So the conclusion here is whichever function we placed in the denominator grows faster than the one we put up here. So I'm going to answer this question by saying 15x plus 3 grows slower than x squared. That's how I would answer the question as it's asked. 15x plus 3 grows slower than x squared as x approaches infinity. So if you had decided to put x squared over 15x, the limit of that as x approaches infinity would have come out to be infinity. And the conclusion would have been the same thing. This is it. This is the answer. That's it.